In our next virtual investigation, we're going to address the syllabus dot point, conducted a practical investigation to explain and predict the motion of objects on inclined planes. So some of the processes that we will use in this investigation are similar to the ones we've done previously, but this time we're going to require a high level of reasoning and problem solving skills. So we're going to be looking at objects sliding down inclined planes, and in this case we're going to assume that it's a frictionless track. So we will use the frictionless track we've got in the lab. So this diagram, it represents what we're going to be doing. So we're going to be investigating the motion of the trolley or cart down an inclined plane, and we've got a constant mass. Now let's have a look at these force components. We'll start with the weight force component, and remembering that equals mass times G, and we've got G is a constant, 9.8 meters per second squared, and this mass is this mass. So now let's resolve this weight force into its parallel and perpendicular components. We've got the parallel force component and the perpendicular force component of the weight force. And our normal force is equal and opposite to the perpendicular force. So we've got an angle here of theta, which is equivalent to the angle here. So I've redrawn the components here. So we've got perpendicular force, parallel force component, which makes up our weight force component. So as usual, I like to talk about, we're going to use trig, so I always write SOHCAHTOA to remind me. And I also like to annotate these. Okay, so I'm interested in this parallel force component because it's the force that's going to accelerate the cart down the ramp. So it's opposite over hypotenuse. So we've got sine theta equals opposite over hypotenuse, which equals the parallel force over the weight force. Rearranging that, we get the parallel force is weight force times sine theta. And I'm going to expand this out a little bit. So our weight force is mass times acceleration due to gravity. And remembering that these two are constant. And now I just want to remind you about the Newton's second law. So this is another form of Newton's second law. If we have a look at it, we've got the force parallel to the plane, which is a force that causes the acceleration parallel to the plane, will equal the mass times the parallel acceleration. So comparing this to over here, we can say that the parallel acceleration equals g times sine theta. So if I write that, so I've now got this relationship where I've now got this relationship where I can say that the parallel acceleration is directly proportional to sine theta. And we've got a constant here, g, equal to 9.8 meters per second squared. So I hope you're all thinking now what I'm thinking in terms of this, that if we graph that and place sine theta here and acceleration here, we're going to get a straight line. And what does that straight line represent? Well, the gradient equals g, which equals 9.8. Well, experimentally we'll wait. So this looks actually pretty straightforward. In the lab, it's easy for us, we can measure the incline angle. So theta, we can measure that by raising the incline of the ramp. And we can use the picket gates on the trolley to measure acceleration with the data logger as well. But you're going to be doing a virtual investigation, which is going to take an approach which is slightly different. In the virtual lab, they're going to run an object down an inclined plane, and they're going to have it roll down over a certain displacement of, say, 1 metre, and they're going to measure the time it takes for it to cover that distance. And they use the second motion equation to do this. So we've got the second equation equals that, and they're going to start the trolley from 0 initial velocity. So we can take that out, and this reduces to this. Okay, a rearrangement of that will give us an acceleration, and we're talking about the parallel acceleration, will be 2 times the displacement divided by the time squared. So they have a known, they're going to use 1 metre for a displacement, and they're going to measure with you can use data logging equipment to measure the time, which they do. Okay, but we're just going to use the simulator. So so this one gets measured. And then from that we calculate acceleration. So this is the inclined plane virtual lab. So you'll have a fixed mass. So I suggest, possibly that's a good one. So that'll be 1 kilogram. And we're going to increase the angle of inclination 5 or 10 degrees at a time. So increase the angle of inclination, say, by 5 degrees each time. Okay, so that's what that looks up. I'll just bring up the data, the spreadsheet. And just to save time, I'll give you a copy of this. So, so we're going to increment by 5 degrees each time. In spreadsheet, remember, we need to convert the degrees into radians before we do sine theta. Okay, we've got a constant displacement of 1 meters, and so you're going to run the simulation, and you can do it just once. That's fine for this. We're going to determine the time it takes to run that distance or displacement. This calculates the time squared, so it takes the square of the time. And then we've got our acceleration, which according to the equation I just showed you is, so this is parallel acceleration, will be 2 times the displacement over t squared. So that formula is in here. And so then the last step will be plotting your acceleration, parallel acceleration against your sine theta. And recall that the relationship for that is we've got parallel acceleration equals g sine theta, and we've got this direct proportionality, we're expecting a straight line, which we will get, and the gradient in this case should be an estimate of G, okay? And that's our gradient there, well, when I did it. So it's close if we take G and round it up to 10. So let's run this first lab. So I've set the first increment, the first angle to 5 degrees. I'll run it. So it takes off. It's covering a distance of 1 metre. And then we scroll down to have a look at the graphs. Okay, we'll use these graphs to work out the initial time, final time, and then the change in time that occurs to cover that distance. So 2 graphs are produced. You've got a position versus time graph, and then a velocity versus time. You can't see the label here, but the x-axis in this second one is time. So this one's probably easier to get the initial and the final times from. So when the trolley started moving, and when it was released, it was 1.5 seconds, and then when it stopped, it's 3 seconds. So I've added some columns there in the spreadsheet that I initially made, where you can record the initial and final time, and then it will calculate the time, the change in time. Okay, so this makes it quite easy. So you just need to enter the initial time, the final time. It'll calculate the change in time, and then calculate the time squared, and then calculate the parallel acceleration. And the graph will be done automatically again, just to save us time. So I think that's enough for you to get going. And what I'll do is put together a second video in terms of evaluating and doing the further data analysis and evaluation of the results.